Yeah, so first thing we'll do, very fundamental stuff. We're going to do exponents and properties of exponents. And by the way, I do recommend if you have some paper or like a notebook to take notes. There are a lot of benefits of note taking. So yeah, so I do recommend taking note. All right, so let's start off. So first thing we will do is properties of exponents, okay? All right, so something I'm going to do a lot in these notes, I'm going to write something called DEF with a colon, and that just means I'm going to put a definition, okay? So this always means a definition of some word is going to follow. All right, just so we know what's up. So that's what that means. All right, so here we go. Here's the first definition. So in the expression x to the m, we call x the base and m the exponent. All right, so I'm sure a lot of you guys know this. Okay, so that's just the terminology. And when m is a positive whole number, this thing we have written here, x superscript m, this is defined to be, okay, well, it's what you think it is. It's going to be x to the m, it's going to be x multiplied by itself m times, all right? So we're looking at m times here, okay? So it's like 2 squared is 2 times 2, so you multiply it by itself m times. All right, so I hope we're all good with exponents. All right, so we have some nice rules and properties of exponents that we're just gonna run through now, okay? All right, so the first thing is called the product rule, okay? Product rule. So very fundamental stuff. So let's just get some motivation. Let's look at x to the third times x to the fourth, okay? So by definition, this is going to be x multiplied by itself 3 times for the first guy. And then the second thing is going to be x multiplied by itself 4 times. Okay, so I hope you guys see how I'm getting this right-hand side. Okay, but now I can just group together everything, and this is the same as x to the 7th. Okay, and it's x to the 7th because I have 7 factors of x appearing. Oops. Okay, so look, I have 1, 2, 3, 4, 5, 6, 7. That's why I have an x to the 7th there. And we could have gotten this even quicker just by doing x to the 4 plus 3. Okay, so this leads to the following rule. All right, so this leads to the following rule. This leads to the following rule. All right, and here is the product rule. It states that a to the m multiplied by a to the n, we can do this very quickly. This is just a raised to the m plus n, okay? So when we multiply 2 exponents with the same base, you just add up the powers. And that's what we did here. Sorry, I don't know why this keeps scrolling down. So I just took m and n and I added them together. That is the product rule, okay? So it's very nice, not that hard. So let's do some examples that use this rule, all right? So here's another thing, another convention in my notes. Whenever I write EX parenthesis, that just means we're doing an example. All right, so let me just write that. EX means example, okay? All right, so let's do one. So let's look at t to the 5th multiplied by t to the 3rd. Okay, so product rule tells us that I should add these exponents. I should do t to the 5 plus 3. Okay, that's what the product rule tells us. I add the exponents, and 5 plus 3 is 8. So this is just t to the 8th, right? So please stop me or raise your hand. I think Zoom has a raise hand feature if you want me to slow down or if you want me to explain something. All right. All right. So I'm going to keep going. If no one has any questions, let's look at another example. Let's look at -2 multiplied by -2 to the second power. All right, so by the product rule, this is really the same thing as -2 to the 1 plus 2 power. Okay, because really there's an understood power of 1 hanging out on that first factor. We just don't write it. Okay, good. And now just add up those exponents. This will be -2 to the third power. Very good. And if you want, we can just finish this off since we're dealing with an actual number here. If -2 to the third power is actually -8. All right, so I hope we're good. Hope we're all good. Let's do one last example. Let's look at x to the second multiplied by x to the fifth multiplied by x to the third. Okay, same deal. Since these are all the same base of x, we can just apply the power rule. Okay, so this is just going to be x to the 2 plus 5 plus 3. Just added all those exponents. That's it. So you just work out that addition of the 3 numbers. That's just x to the 10th. X to the 10th. All right, so I hope everyone's okay. I see something in the chat. Yeah, so I'm not gonna be able to look at the chat the whole time, so maybe if you just wanna, if you can talk on the mic. But so someone asked how it's -8. So this is -8 because if I multiply -2 by itself 3 times, well, -2 times -2 is 4, and then 4 times -2 is -8. Okay, so someone asked why this was -8, and that's why. Okay. All right. All right, so I will move along if everyone's okay. All right, so next rule, very similar to the previous one. This one's called the quotient rule, okay? Quotient rule. Okay, so we're still dealing with properties of exponents here, okay? All right, anyways, so let's just look at some motivation like what we did with the last one. So let's consider y to the 4th. So we're doing a quotient, which means we're going to be dividing numbers. Let's look at y to the 4th divided by y to the 3rd. Well, if I just write this out in an expanded form, this is y times y times y times y in the numerator, because that's the definition of y to the 4th, just y multiplied by itself 4 times. And in the denominator, we have a similar thing. We have y multiplied by itself 3 times. Well, that's cool because now we have a bunch of cancellations. Okay, so this y and that y cancel, that y and that y cancel, that y and that y cancel. Basically, we're just left with y to the 1st. And if you're clever, you can rewrite 1 as 4 minus 3. And how did we get those numbers? Well, I just took the power in the top and the power in the bottom. So this leads to the rule, the quotient rule, okay? So basically, you just subtract the powers instead of adding them. All right, so here's the quotient rule. This leads to, so let's look at a to the m divided by a to the n. This is, why is it doing that? I'm sorry, my thing keeps like zooming in and out, and I have to figure that out. Anyways, this will be a to the m minus n. So we subtract powers when we divide. All right, and let me just make a quick note that here we're just supposing that m was greater than n, just so we end up with a positive exponent. because we don't know how to deal with negative exponents yet, but we will very soon. Okay, so that's the rule. It's very similar to the product rule, except now we're subtracting. So I hope we're okay here. All right, so please just stop me at any time. All right, so let's just do a few examples. So let's look at b to the 7th divided by b to the 2nd. Okay, so the quotient rule tells us that I ought to subtract those powers. So I did 7 and I did -2 because those are the powers that appear. And now this is a simple affair. 7 minus 2 is 5. So we just have b to the 5th. All right. So far, so good, I hope. Last example under this rule, let's do 3 to the 1001th power divided by 3 squared. All right, so we're getting a little crazy with the numbers here. But really, nothing has changed. We're just going to subtract these two numbers. Okay, so the quotient rule tells us this is the same as 3 to the 1001 minus 2. All right, so look, 1001 went there and 2 went there, and I'm subtracting because we're dividing. Excellent. And this is, this is 3 to the 999th power. All right, and you can leave it like this because that's a crazy number. Probably, I didn't work it out, but yeah. So that's that. All right. So if there are no more questions, if there are no questions, I'll go on to the next rule. All right, so just please let me know. All right, next rule. This one is called the power rule. Power rule. All right. Power rule. So this is the case when we have an exponent itself raised to a power. Okay, so how do we deal with that? So again, let's look at a little motivating example. Let's look at, so I just like to do a motivating example, then I introduce the rule just to see where it comes from. All right, so let's look at x squared cubed. That's what this rule will tell us. This is what the rule will, how to deal with an expression like this. That's what the rule will tell us. So by definition, this is x squared multiplied by itself 3 times. So xx times xx times xx. Okay, I hope that's okay. I just put an x squared multiplied by itself 3 times. And now you can just visually see that this is the same as x to the 6th power. Because you count all the factors of x there are 6 of them. Okay, but how else could we have arrived at 6? Does anyone maybe want to tell me how I could have gotten 6 from this?
You multiply.
Yes, I heard 2 people say it. Thank you. Yes, exactly. You multiply the powers. 2 times 3. There we go. So now we're good. So now you guys know the rule. So this leads to, so I just like to show you guys where the rule is coming from. I'm not just pulling it out of thin air. Yeah, so this leads to the product rule. No, power rule, sorry. This leads to the rule. Here we go. A to the m, that whole quantity to the nth. Okay, so I have an exponent raised to a power. This is nothing other than a to the m times n. Multiply the powers. Okay, that's it. That's the rule. All right, so let's do some concrete examples. So how about this? How about x squared to the 7th? Okay, that's not too bad. All we need to do is multiply, excuse me, we just need to multiply 7 and 2. That's what the rule tells us. So this is x to the 7 times 2. And that's an easy thing. That's just x to the 14th, yes. Okay, So that would be the final answer there. So just one more, or yeah, and then let's look at one more example. So how about this? How about 4 to the 10th power? That whole thing raised the third power. Okay, not that bad. The power rule just tells us I ought to multiply those two numbers. Okay, so that will be 4 to the 10 times 3. Correct. And that's just 4 to the 30th, because 10 times 3 is 30. All right, so are we good here? So yeah, so please just let me know if anything is weird or not clear. I'll be happy to explain, really. But yeah, I will move on if we're good. Okay. All right. So I think someone's mic is unmuted. If you could just mute it for me, thank you. So I don't really mind. It's just like a little distracting. Okay. So next rule. How about this one? This one's cool. This one is called the zero exponent rule. All right. So really we're going to answer the question, what does it mean to have an exponent of 0? That seems kind of weird. So let's look at a motivating example. Let's look at this. Let's look at y to the 5th divided by y to the 5th. Okay, so we're dividing something by itself. I hope you guys agree. The numerator and the denominator are exactly the same. So that means it's going to be 1. Okay, anything divided by itself, they just cancel to 1. However, on the other hand, using the quotient rule, well, we do have a quotient. We have a y to the 5th divided by y to the 5th. The quotient rule tells us I should subtract the two powers. So let's do that. This is totally fair. This is totally valid. So y to the 5 minus 5, and that's y to the 0. Aha. So we have arrived at two different expressions for y to the 5th divided by y to the 5th. So basically we conclude that y to the 0 is 1. So we looked at it from two different viewpoints. So that's motivation as to why we define the 0th power to be 1. Okay, so this leads to, so what's the conclusion here? This leads to, yeah, so someone's raising their hand. Just give me 1 second. Let me just write this. So this leads to, so a to the 0th power equals 1. Okay, for any non-zero real number a. All right, so that's the rule. That's the rule. Anything to the 0th power, anything that's not, so you need to say that a is not 0. So any non-zero number raised to the 0th power is 1. Okay, so this, I think some people have some questions, so just go for it. I don't know who exactly had questions.
Yeah, I'm gonna go. I don't know if there's anyone else, but if something is like multiplied, it's not multiplied by itself because it's like the exponent is 0. So like if it doesn't multiply by itself because it's 0, it's not multiplying. So isn't it 0? Like I was a little bit confused. Sorry.
I know, that's a totally great, like, that's an amazing question. So that rule, so that definition we had for the exponent, when we multiply it by itself that many times, that was defined just when the exponent was a positive number, like 1, 2, or 3. 0 is neither positive or negative. So we're actually this is actually like a new definition. Yeah, so we're just kind of like,
Thank you.
Yeah, no problem. That's a great question. Yeah, so we're just like making a to the 0 be 1. And this is kind of motivating as to why we do it by this calculation up here. So this is actually more of a definition and not a rule. But very good, good, good.
I
All right.
had a question.
Yeah, sure.
So if y is to the power of 0, could it also just be y, like without an exponent?
No, I see what you're saying. No, y without an exponent is understood to be y to the first.
Okay.
Yeah, y multiplied by itself one time. So we have
Okay.
one factor of y hanging out there. Yeah, good, good. All right, good. So let's just do some examples using this rule, and then we'll move on. Okay. Yeah. So just recall whenever I write ex, that just means example. Okay. Okay. How about this? How about c to the third divided by c to the third? Well, we can just use the quotient rule on that. That's just c to the 3 minus 3. 3 minus 3 is 0. And we know now that c to the anything to the 0th power is 1. So that's kind of easy. And you could have seen this just by anything divided by itself is 1 as well. But it's like a new lens to look at it through. All right. What else do I have here? No, I don't want to do that one. Okay, how about this one? This one's cool. So how about k multiplied by k to the 4th divided by k to the 5th? That's interesting because we need to use one of our rules in the numerator. Okay. So I have a k multiplied by k to the 4th. So what does the numerator become? Well, I hope you guys agree that the numerator will become k to the 4 plus 1. All right, so I'm using that that product rule there in the numerator, okay? And the denominator will stay just as is, k to the 5th. Now we can keep going here. This is k to the 5th divided by k to the 5th. And that's k to the 0. That's 1. Okay, so what was interesting about this question is that from here to here, I was using one of our previous rules. I was using that product rule, all right? So that's why the numerator changed to this guy. All right, so I hope that's okay. Awesome. And last one, how about this? So this is kind of just to show you the rule. So x plus y plus z plus 1,000 plus 7 to the 0th power. This is 1. Okay, no matter what I put inside this parenthesis, as long as it's not 0, as long as the parenthesis isn't 0, the answer will be 1. All right, so I was just kind of being a little silly there, but I was just like making a point. Anything to the 0th power is 1. All right. Okay, awesome. So I will move on to the next rule.
I just have a quick general question, if you don't mind.
Yeah, of course.
Hopefully it's not like kind of getting off topic, but is there any type of order of operation that would lead to us dividing exponents? I know we are adding, multiplying, and subtracting, but I didn't see one where we would divide. So that's all.
Yeah, so that would have worked, like if you kind of did this k to the 4th divided by k to the 5th first, and then you multiplied it by k, you would have gotten the same answer. So if that's kind of what you're asking, order of operations won't be that, I don't think it will be much of a problem. I think you can kind of do it in any way you want and it should work out. But we'll see as the questions get a little more complicated. Okay, all right, so that's that. Next rule, so this is cool. So how about negative exponents? Okay, so far our exponents have been 0 and positive. How about negative exponents? Let's look at that. Rule of negative exponents. Alrighty, so I'm gonna motivate this again. So how about this guy? Let's look at h to the 3rd divided by h to the 5th. Okay, So just by definition of the exponent, this is going to be h multiplied by itself 3 times up in the numerator, and the denominator will be h multiplied by itself 5 times. Very good. And then if you just cancel this out, you just cancel out your factors of h, you'll see that you'll end up with 1 over h squared. All right, so I hope you guys see that. So I cancel h, h, h. I'm left with 2 factors of h down there in the fraction, okay? Good. But on the other hand, so it's kind of the same thing as before. On the other hand, we can use the quotient rule in this. On the other hand, h to the 3rd divided by h to the 5th. Well, this was h to the 3 minus 5. Okay, and 3 minus 5 is negative 2. Aha, so we have arrived at 2 different answers for the same thing. So pretty much what this tells us is that we want to make h to the negative 2 equal to 1 over h squared. We ought to have those be equal to each other. Okay, so that's what the following rule is. It says, so this leads to the following rule. Okay, so this is the rule of negative exponents. Pretty much a to the minus n. Okay, this is just 1 over a to the positive n. Okay, so you just bring the term into the denominator and the exponent becomes positive. That's what the rule is. So this is actually a definition, okay? This is a definition. All right, so I hope everyone's okay with this. A to the minus n is 1 over a to the n. All right. You have a question?
Yeah, sorry, I keep asking questions, I'm sorry. But if there's a negative exponent in the denominator, does it like turn again or?
Yeah.
Okay, yeah, thank you.
Great question. Yes. So what she's asking is, what if I have like 1, yeah, that's an excellent question. What if I have 1 over a to the negative n? What is that? Well, this is actually just going to be a to the positive n. Okay, and you can show this. Let me. How would this work? I'm just trying to think of a way to prove this right now, but I'm on the
So is the rule just like always whenever there's a negative exponent, you're gonna flip it basically over like?
Yes.
Okay.
If you bring it from the top to the bottom, make it negative.
Okay.
Also, if you bring it from the bottom to the top, make it negative.
Okay.
Doesn't matter which way you're going, top to bottom or bottom to top, negate that exponent.
Okay.
And that's what this is, and that's what these 2 things are telling us. I brought it upstairs, it became positive, and I brought it downstairs and it became positive.
Okay.
Very good. Awesome, awesome. All right, so that's the rule. And again, let's just do some examples. So how about this? P to the 3rd divided by p to the 10th. Okay, that's going to be p to the 3 minus 10 by the quotient rule. Okay, and then 3 minus 10 is just negative 7. Good, and now the next equal sign, I will apply the rule. So bring that into the denominator. That'll be 1 over p to the positive 7th. Okay, I brought it down, so I made the exponent positive. All right. So I hope that's okay. And let's do one more here. Okay, nice, yeah. So let's look at z to the 2nd multiplied by z divided by z to the 4th. All right, so with this one, in the numerator, I hope you guys will agree that that numerator becomes z to the 3rd. And why is that? Well, I'm just going to add up the powers. 2, and there's a power of 1 there. That's just understood. So that's z to the 3rd. And the denominator stays as z to the 4th. Excellent. Now, use your quotient rule. This is z to the 3 minus 4. 3 minus 4 is negative 1. And now we use the rule of negative exponents. Bring it down, bring it into the denominator, that's 1 over z. All right? So hope that's okay. Let's see, so I think that's it for negative exponents. Yes. All right, so just please stop me if anything's weird or not clear. All right. Good, good, good. All right, so next rule. Yeah, so we're just gonna chug along here and just trying to get all these rules out of the way. All right. Next one. The power of a product. Okay. The power of a product. So first of all, what is a product? Well, a product is just when you multiply two things together. Like 2 times 3, that's a product. Okay. A times B, that's a product. What happens if we raise a product to a power? How do we deal with that? And that's what this rule will tell us. All right, so here's some motivation. So say, so this is not the rule. I'm just doing like the motivation first, then I'll get to the rule. So say we want to simplify this guy. Let's look P times Q to the third. Let's just say we want to do that. So PQ is a product because it's two things being multiplied together. So we have a product raised to the power of 3. Okay, so by definition, this is just PQ multiplied by itself 3 times. Okay, that's just straight up from the definition. Excellent. Okay, so now I'm gonna be a little fancy. I can get rid of the parentheses. So PQ, whoops. So I'm just gonna get rid of the parentheses. PQ, PQ, PQ. And this is the reason why I can do that. That's by the associative property of the real numbers. Okay, I wouldn't worry too much about that. But that just says I can group the terms in any which way I want. So this equal sign is just by the associative property. All right, but I wouldn't worry too much about that. Next, I can rewrite this as P times P times P times Q times Q times Q. So I've kind of I've moved that P over and that P over. I've just reordered the terms. So does anyone know by what property that follows by? Does anyone know what that property of the real numbers is called? I can switch the order of multiplication.
Isn't it the commutative property?
Yes, yes, excellent, thank you. So that follows from the commutative property, all right? So don't worry about that. I'm just trying to justify why I'm allowed to do these things, okay? Finally, this is, I hope you guys agree, that first grouping of P's, that's P to the third. Second group, and that grouping of Q's is Q to the third. Very good. So you can see what happened here. I essentially just distributed this 3 to both factors of the product. And that's the rule. That's the rule. Okay, so let's just formalize it. So this leads to the rule. All right. So the rule tells us that the product, AB, that's a product, raised to the nth power. This is the same as A to the n multiplied by B to the n. All right, so I really like this rule. This is a really useful thing. So really what this is telling us, I can just distribute the power to both factors of the product. Excuse me. All right, so I hope that's clear. And we're just gonna do some examples, okay? All right, so how about this? How about xy to the 7th? Okay, let me just apply that rule. I'm gonna bring this power of 7 to each factor. So this is x to the 7th multiplied by y to the 7th. Okay, so I hope everyone can see that. How about this one? How about this one? How about 3 times z times w, that to the 2nd power? All right, let me just raise each factor to the 2nd power. That's what the rule tells us. So that's 3 squared multiplied by z squared multiplied by w squared. That's it. And if you want, you can rewrite this 3 squared as a 9, but whatever, you don't need to. So that's that. And let's do one more slightly more interesting example. How about this? How about f to the minus 2 power multiplied by g multiplied by h to the third. That whole thing to the third. Okay, so let's just take a breath. We're just going to use the rule. I'm just going to bring this power of 3 to each factor as the rule tells us. That's it. So just by the rule, this is going to be f to the negative 2 cubed to the third power. Brought it to that guy. Next, bring it to g. G to the third power, and h to the third power to the third power. Okay, I just brought that power of 3 to each factor. Now, what's very cool is that we have rules to deal with this guy and that guy. We know how to deal with those now. And that was the power to a power rule. You just multiply the powers. Okay, so I hope that's cool. So this is going to be f to the minus 6, because that's what 3 times negative 2 is. Okay, the g to the third can stay, and h to the third, that whole thing to the third power, that's h to the 9, because 3 times 3 is 9. All right, and so this was by power rule. That's how I got to this equal sign here, okay? So from here to here was by just our previous power rule. Okay, so I hope that's cool. So like these are the kind of questions you'll see on the first homework, like just kind of simplifying expressions using our rules, all right?
Is the homework gonna be from like the textbook?
No, so I'm writing all the homeworks. I'm gonna post a PDF file after this class with the homework.
Okay.
Yeah, so it's just gonna be a file and you'll just see it on the PDF.
Are we ever gonna really need the textbook or no?
Not really. No, you probably just as like a second reference.
Yeah.
If you want like some other viewpoint, but yes.
Okay.
Will the homework be like you can write on it and just submit it like that, or do you have to write on a different paper?
It's going to be on a separate piece of paper.
Okay.
Yeah, because the homework just has like a bunch of questions, like with like no space in between them. There's no space in between the questions. It's just like a list of questions, pretty much. Just do it on a separate sheet. Yeah. So I'm going to post that homework after tonight. You'll see it. All right, cool. So we just did the power of a product. The next natural thing to look at would be the power of a quotient, so the power of a fraction. Okay, so that's the next rule. So this is called the power of a quotient. So just recall that a quotient is just dividing two numbers. So A divided by B, that's a quotient. So we're going to look at a quotient raised to a power. So I'm actually just going to jump straight to the rule in this one. It's a bit on. Hold on. I'm just going to jump straight to the rule here. All right, so the rule is, it's just A over B. So the division of two numbers, a fraction, if you will, to the nth power. This rule will tell us that this is A to the n divided by B to the n. Okay, so I just am distributing the power to the numerator and denominator. That's really all that this rule tells us. Yeah, so the textbook is free. Yeah, it's just a link. It's just like an online. Yeah, so someone in the chat asked if the textbook's optional. No, you don't even need to buy it. It's just like an online textbook. Okay. Good. So, so what's interesting about this rule is that we can actually prove it. We can do like a very quick proof. So I know some people have some very negative memories attached to the word proof, maybe from high school geometry. The proofs aren't that bad. So we can do this one. All right, I promise. So let's start with the left-hand side. of the equal sign, okay? So a over b to the nth power. Okay, so do you guys agree that I can rewrite the parentheses, the thing that's in the parentheses, as a multiplied by b to the minus 1 by properties of negative exponents? Dividing by b is the same thing as multiplying by b to the minus 1. Okay, so that's what I did. I rewrote a over b as a multiplied by b to the negative 1. Okay, good. Now I have a product raised to a power. I can move this n to each guy here by the product rule. Okay, so this is a to the n multiplied by b to the minus n. Right? Because I multiply -1 by n, I get negative n on that guy. So this was by the product, I think the product rule. Yeah, that's what we called it. Okay, so does anyone see the last step? How do we get to this guy? So does anyone want to maybe tell me how to get to the conclusion of the rule?
You're gonna make it a fraction since it's a negative exponent. And since you're multiplying the numerator by 1, it's gonna be itself.
Yes, exactly. So using properties of negative exponents, exactly, I can make this b to the minus n, b to the positive n, just by bringing it into the denominator. Okay? So that's it. So that's the proof. So I don't think that was that painful. All right, so that's the proof. And also, you won't ever have to do proofs on homework or tests. That's just for fun. Okay, so let's see this. Yeah, so it is hard for me to answer questions in the chat. So if, just because it's not on my screen. But why is the b negative? So Chanel, what do you mean? Why is the b negative?
What I mean is, like, how did you get it from being a positive b to a negative b? Why is the a negative as well?
Okay, because the a was in the top of the fraction, so that just stayed. And 1 over b is the same thing as b to the minus 1.
Oh, okay, thank you.
Yeah, so this over b part, I have just rewritten as b to the minus 1. Okay. That was just proper. That was just our negative, excuse me, that was just our negative exponent rule. Okay. So that's the proof. Let's do, yeah, I think it was like one example of this. So let's just use this guy. So let's do 4 over z to the 11th. That whole thing raised to the 3rd power. Okay. Okay, so the quotient rule tells us I can just raise the top and bottom to that power. So this would be 4 to the 3rd over z to the 11th to the 3rd. Okay, so I just used the quotient rule. I moved this power of 3 to the top and bottom. But what's cool is that z to the 11th to the 3rd in the bottom, I can use the power rule on that. I can just multiply the 2 powers. Okay, so that's going to be z to the 33rd. Okay, and that's by, so I'm just getting confused with all the names. That's the power rule, yeah. Okay, so that just tells us if I have a power to a power, I can multiply the exponents. All right. So that's that. Okay, cool. So let's just go through some, so now let's look at like some practice problems that you would see on the homework. So this part is just called simplify exponential expressions. Using previously learned rules. All right, so we're just gonna use everything that we just learned to simplify some expressions using previously Previously learned rules. All right. All right. So let's see what this looks like. Let's look at 2u v to the minus 2, that whole thing to the negative third power. Okay, so there's a few ways you can attack this. You can make the exponent positive immediately by bringing it down, but how about we just distribute the power to each factor? So let's use the product rule, okay? So this would be 2 to the minus 3 multiplied by u to the minus 3 multiplied by v to the negative 2, that whole thing to the minus 3. Okay, so this was by the product rule. All right, so I hope everyone sees how I got that. I'm just putting this power of minus 3 onto each factor as per the rule states. Okay, very good. And now let's use our negative exponent rules. So this will be 1 over 2 cubed multiplied by 1 over u cubed multiplied by v to the sixth power. Okay, so I just made all of those exponents positive. So hope we're good. And now we're pretty much done. We can just add these fractions together. I mean, multiply these fractions together. This will be v to the 6th divided by 8u to the 3rd. All right, so does everyone, I hope everyone's okay from here to here. I just multiplied the fractions together. Okay. Okay, so we're gonna look at now square roots, okay? Square roots. All right, so we're gonna have a definition. I'm going to define what a square root is. So I'm going to write DEF. So just recall, DEF just means I'm going to put a definition. Okay, I'm going to define some words. Okay, all right, here we go. Here we go. So it's a little bit of writing here. Okay, so the square root of a positive number. Okay, denoted as, I'm sure you guys are familiar with this notation, denoted as that, this symbol, denoted as that. Okay, what does this mean? Is a positive number such that when multiplied by itself, is a. Okay, so I know that sounds kind of weird, but if you think about it, that is what a square root is. Okay, so just a quick example, square root of 9, we need to find a number such that when you multiply it by itself, you get 9. Well, doesn't 3 work? If I multiply 3 by itself, I will get 9. So thus, the square root of 9 is 3. All right, so I hope that's cool. All right, so just some terminology. I know this is not the most fun. So terminology, so we just need to give some words to these symbols. So in the expression, square root of a, this symbol is called a radical, okay? And that number underneath the radical, and a, is called the radicand. Okay, so that's what we're defining. Radical is this symbol, and that thing underneath the radical is called the radicand. Okay, very good. Cool. All right, so just now, before we go on to some examples, let me just do a quick warning. So here's the thing. does the square root of 25 equal 5 or negative 5? So we need to be very careful here. What does it equal? And the answer is it's 5, okay? And the reason being is because if you go up to the definition of the square root, you take it to be the positive number, such that when you multiply it by itself, you get back a. Okay, so we're always looking at that positive branch of the square root. Okay, so it is 5. Okay, so I hope that's cool. All right, here we go. So let's do some examples. Okay, so square root of 100. This is 10 because if I square 10, I get 100. I get back what's underneath the radical. All right. How about this? Let's look at the square root of 25 plus 144. So if you just add up these two numbers, you'll get the square root of 169, and that is 13. Reason being, 13 squared is exactly 169. Okay? That's all we're doing here. We're just finding a number such that when you square it, you get the thing under the square root. And 13 does the job. Okay? All right. Last example, square root of 81 minus square root of 49. So the square root of 81, that is 9. And the square root of 49 is 7. Okay, so I hope that's okay. And that is just going to be 2. All right. So just any questions, just please let me know. Okay, so I need to give you guys another warning. Okay, it is not true, okay? It's not true that the square root of a plus b equals the square root of a plus the square root of b. Okay, this is not true. I've seen this mistake a lot, like even when I taught Calc 2 in these upper level courses, I've seen students make this mistake. So let's not make this mistake, okay? This is not true, all right? So you can't break up square roots with addition, okay?
Can you scroll to the right a little bit?
To the right. Is part of the screen missing?
Wait, hold on, maybe if I can turn this way. No, it's okay, never mind, I got it.
Okay. Yeah, so that's the deal. However, we can split square roots up via multiplication. So that's the next thing. All right, however, okay, so just please note this warning, but we do have some consolation. However, we do have the following multiplicative property. We do have the following multiplication property. All right, and here it is. So this is also called the product rule. So I know we're overloading our terminology here, but so here's a product rule. It states that for positive numbers, a comma b, we have. Okay, so we can split the square root into products. So all this means is that the square root of the product AB, this is equal to the square root of A times the square root of B. Okay, so is everyone okay with this? This is pretty much saying that the square root of a product is the same thing as the product of the square roots. All right, so that's very useful. So we use this property. We use this property to simplify radical expressions, okay? Okay, like as such. So let's do some examples with this guy, like as such. Okay, so here is the example. So let's look at simplify the square root of 300. Okay, so I will tell you guys the set of steps, but just kind of hear me out for a second. So you guys, I hope you guys will agree that the square root of 300, this is the same thing as the square root of 100 times 3. Okay? 100 times 3 is 300, so I didn't do much. Now I will use the property of breaking this up into two radicals. This is the same thing as the square root of 100 multiplied by the square root of 3. Okay, so does everyone see how I went from here to here? This is by the property, okay? And then now the square root of 100 is 10, so this is 10 square root of 3. Okay, so that's kind of how we use this property in practice. It allows us to simplify these radical expressions. So here are the set of steps. So here are the set of steps for simplifying a radical expression. Okay, so here we go. Step one is to factor any perfect squares from the radicand. Okay. So that was when we factored out that 100 from 300. 100 is a perfect square, so that was that part. Step two is use the property to rewrite the radical as a product of radicals. Okay. And we did that when I rewrote the square root of 100 times 3 as the square root of 100 times the square root of 3. Okay? So that was that part. And the final step is to just simplify. So basically just simplify your perfect squares that you have factored out. Okay? So let's actually just use these set of steps. It's much clearer when we see it in a concrete example. All right. So let's look at, so the task will be to simplify the square root of 27. Okay, so step one, I'm going to go in coordination with the steps. So step one was to factor any perfect squares out of the radical. So I hope you guys agree that the square root of 27, this is the same thing as the square root of 9 times 3. And I wrote it as that because 9 is a perfect square. Okay, so that was step one. Step two of the procedure was to rewrite this guy as a product of two radicals. So step two, you rewrite square root of 9 times 3. This is the same as the square root of 9 times the square root of 3. Okay? So that was step two. And step three was to just simplify. Okay, so square root of 9 times the square root of 3. This guy, square root of 9, that just simplifies down to 3. So this is just 3 multiplied by the square root of 3. All right, and that's the final answer. All right, so I hope that was okay. So these numbers I have, this follows the set of steps from earlier. Okay, that's what these numbers are. All right, so the answer is 3 times square root of 3. All right, let's keep going. So next example. Let's simplify the square root of 48. Okay, So really what we need to do here is we need to factor a perfect square from 48. So that's probably the only part of this that takes a little bit of thinking. We need to think how we can rewrite at 48 as a perfect square times some other number. But that's not that bad. So square root of 48, 48 is the same as the square root of 16 times 3. Okay? And why did I do that? Because 16 is a perfect square. So that was step 1. Step 2, I rewrite that guy as a product of 2 radicals. That's square root of 16 times square root of 3. Okay? And then the final step is to just simplify. So square root of 16 times the square root of 3, that is just 4 multiplied by the square root of 3. Okay? So that's the reason why we want to factor a perfect square out, is so this thing will simplify pretty nicely. All right, so I hope you see why we're doing these things.
Hey, Professor, just a really quick question.
Yeah.
I see that we're taking like pretty much the biggest square root that we can. So, example, if we were to take 4 square root of, what would that, 12, that wouldn't break down to the same thing, would it? Or, well, yeah, so 4 square, because 4 is a perfect square as well.
Right.
So it couldn't be 2 square root of 12, could it?
So you're looking at 4 square root of 12?
Yeah, no, well,
or just square root of 12 by itself?
The square root of 4 times 12.
Okay, square root of 4 times 12. Yes, so that will work. You just may need to use the procedure again on this guy, on the resulting radical.
Yeah.
Got it.
So, yeah, so you want to try and factor out the biggest perfect square, like we were doing. But if you factor out a smaller one, that's okay. You just need to you may have to repeat the process on the resulting radical.
Good. Thank you.
Yeah, of course. Good. All right. So that's that. So this was the power rule. We're just going to quickly do the quotient rule, okay? And this is pretty easy. So similarly, we have the quotient rule. Okay? So this is just saying that the square root of a fraction, the square root of a quotient, if you will, is nothing other than the square root of A divided by the square root of B. Okay, so you can see that these rules are very similar to our exponent rules, okay? And there's a reason for that, actually, which we'll get to. Okay, so the square root of a fraction, you can just bring that square root into the top and bottom, okay? All right, so let's just look at an example here. Okay, let's look at the square root of 2x squared over 9y to the 4th. Excuse me, that should be a 4. 9y to the 4th. Okay. So the rule tells me that I should just bring the square root into the top and bottom. So this is the same as the square root of 2x squared divided by the square root of 9y to the 4th. Okay, very good. And now we can just simplify. This will become x square root of 2 divided by 3y squared. All right. So I did skip some steps from here to here, but I hope we're okay. If anyone wants me to explain from here to here, please let me know. So pretty much all I would
explain that one.
Yeah, definitely. So just quickly off to the side, the numerator is the square root of 2 multiplied by the square root of x squared.
Okay.
By the property. So the square root of 2 stayed. I kept that. That's right there. And the square root of x squared, well, pretty much x squared is a perfect square. So the number you multiply by itself to get x squared is just x. Okay, that's the square root of x squared. So I hope that's okay.
Okay, got it.
And we did the same exact thing with this square root of 9 y to the fourth. So that was just the square root of 9 multiplied by the square root of y to the fourth. This becomes 3, and the square root of y to the fourth is just y squared. Okay, because if I multiply y squared by itself, I will get y to the fourth. So that's the square root of y to the fourth.
Thanks.
All right, so I hope that's okay. And there'll be some nice practice with this on the homework. Yeah, so you can get these. Okay. All right, good, good. All right, so we're almost done here. I'm gonna try and finish up early tonight. So next, we're just gonna wanna do some adding and subtracting of square roots, okay? So let's just get that. Adding and subtracting. Square. Alrighty, adding and subtracting square roots. Okay, so here we go. So here's the deal. Radical expressions can be added or subtracted. Sorry, or subtracted as long as they have the same radicand. Okay, the same radicand. So that was that number that's underneath the square root. Okay, so here's just a very quick example. The square root of a plus the square root of a. These have the exact same radicand. They both have an a in the square root. So we can combine them. And this is just going to be what you expect it to be. It's going to be 2 square root of a. All right? Very good. How about another example? How about the square root of 3 plus 6 times the square root of 3? Okay, so we just need to acknowledge here that the radicands are exactly the same. So they can be added together. So this is just going to be 7 radical 3. All right, so I hope that's okay. So it's kind of like you're adding like terms, like when you add 2 polynomials together, which we're gonna do that later, but it looks the same as that. So this is 7 square root of 3. All right. So sometimes these questions aren't going to be presented as nicely as they just were. Sometimes you're going to need to simplify the radicals first and then add them. All right, so let me just write that quickly. However, sometimes we first need to simplify the radicals before being able to add them. Okay, and we'll just do a quick example of that before being able to add them. Okay, so let's just see what that looks like. So how about this guy? So how about 5 square root of 12 minus 2 square root of 3? Okay, so upon first glance, these cannot be added, right? Because the radicand here is 12 and the radicand here is 3. We would love to introduce a radicand of 3 somehow. Well, we can do that just by simplifying the square root of 12, okay? So here we go. So first, simplify that first guy. First, simplify 5 square root of 12. Okay, just using our set of steps from before. So 5 square root of 12, this is 5 square root of 4 times 3, which is 5 times the square root of 4. Whoops, hold on. It's 5 times the square root of 4 times the square root of 3. Okay, and the square root of 4 is 2, so it's 5 times 2 times the square root of 3, which is 10 square root of 3. Okay, so I hope that's okay. And now we're in good shape because now our question takes the form. So now it's the same as 10 square root of 3 minus 2 square root of 3. Okay, so I just replaced this 5 square root of 12 with its equivalent expression, 10 square root of 3. That's all that happened. And why is that good? Because now we can actually subtract. Alrighty, so now we can actually subtract them. This is just going to be 8 square root of 3. Alrighty? So someone's mic is on right now. Okay, I think I got it. Okay, so that's the answer, 8 square root of 3. So I hope everyone's okay with what we did here. We first simplified this guy to introduce the same radicand so we can add them together, or subtract in this case. All right, let's move along. Okay, I know there's a lot of stuff going on in this lecture right now. All right, we're almost done here. So here's a very important thing, rationalizing denominators. Okay, so this is big in calculus, so we ought to do it since this is a pre-calculus class. So rationalizing denominators. All right, here we go. So we have a lot of, so I just have some writing to do first. So we're going to start off with the definition. So the conjugate, here we go, the conjugate of a plus square root of b, that's what we're defining, is defined as a minus the square root of b. Okay, so you just take that plus sign, turn it into a minus sign. That's the conjugate of a plus b. Okay, and that's going to be very useful to us. All right, so why do we care about this thing? Okay, let me just write a little bit. So this is going to be very useful in Calculus 1 when you're computing limits. All right, so just to show you, there is a reason why we're doing this. If you are taking Calc 1, this will be useful. Okay, so in calculus, so calculus 1 specifically, in calculus 1, it will, because I imagine some of you guys will be taking Calc 1 next semester, it will often be useful to rewrite expressions such as c over a plus the square root of b by multiplying the top and bottom by the conjugate of the denominator, okay? So as such, so c multiplied by a plus b multiplied by a minus square root of b over a minus square root of b. Okay, so I hope you guys agree. I'm not changing the value of this fraction because I'm multiplying by 1. I'm multiplying by the same thing divided by itself. So I'm really not changing the value of this fraction. We're just rewriting it. Okay, so hopefully this seems a little familiar from high school. I think this is done in some like Algebra 2 classes in high school, okay? So yeah, so we're gonna do this. We're gonna multiply the top and bottom by the conjugate of the denominator. All right.
C is just used to substitute another variable, right? Like, like another unknown value.
Yes, C is just just a number.
Okay, this one.
Yes, exactly. Good, good. Yes, I should have been clear about that. Yes. So let's just do an example here. So let's just do one example. It's going to be simplify 4 over 1 plus the square root of 5. Okay, so I hope you guys agree this thing does take the form c over a plus square root of b. All right. So what we're told is that we should multiply the top and bottom by the conjugate of the denominator. So we're just going to do 4 over 1 plus square root of 5. We're going to multiply the top and bottom by 1 minus the square root of 5. 1 minus the square root of 5. Because that's the conjugate of the denominator. Look, this plus sign has turned to a minus here. That's the conjugate. All right, and this is good. So this will just turn out to be 4 times 1 minus square root of 5 in the numerator, and the denominator just comes out to negative 1 minus 5. This is 4 times 1 minus square root of 5 over negative 4, and this is just negative 1 minus square root of 5. All right, I moved very fast there, but so does someone have a question? I think I saw a question.
Yeah. Could you define what a conjugate is?
Did I define what a conjugate is?
Could you do it again? I'm sorry.
Oh, yeah,
I
sure.
did it, but I just missed it.
Yeah, so the conjugate of a plus square root of b is defined to be a minus square root of b.
Okay.
Yeah. So here we took 1 plus the square root of 5, and we multiplied the top and bottom by the conjugate of this guy. And the conjugate of this guy is just 1 minus square root of 5.
All right. Thank you.
Yeah, no problem. All right, and the reason why we like to do this is because it gets rid of square roots in the denominator, which when you compute limits is not a great thing. So that's further along in your mathematical careers if you guys do go further. Okay. So that's that. So you can simplify this a little more. You can distribute the negative 1 into this. So it'd be negative 1 plus square root of 5. Okay. So that would be useful to you guys if you take Calc 1. Alrighty. So that's conjugating. There's going to be a question on the homework where you have to do this. Okay. All right. Very good. Very good. All right. So next, we're going to look at nth roots. Okay. Nth roots. We did square roots. We would like to generalize this to nth roots. Okay. So here we go. Here's the definition. Okay, the nth root of, so the nth root of a, which is denoted as such, it's denoted as this symbol. Okay, it's like a square root, but we put an n in that little nook there. Is a number is a number such that when raised to the nth power is a. Okay, so we're just kind of generalizing the square root now to n, to the nth, to an nth root. Okay, so it's a number such that when you raise it to the nth power, you will get back this thing underneath the radical. All right, so let's do some examples. So example, how about the third root, or the cube root, which you call it sometimes, of 8. Okay, so this will be 2 because if I raise 2 to the third power, I get back exactly 8, which is that number in the radical. So I hope that's cool. How about this? How about the fifth root of negative 243? This will just be negative 3 because, and the reasoning is very simple. If I raise negative 3 to the 5th power, if you just work that out, I will in fact get negative 243. Okay, that's literally the definition of the 5th root. If I raise it to the 5th power, I will get back that thing in the radical. Very good. And let's do one a little more trickier. How about the fourth root of 48? Okay, so I'm going to rewrite this guy as the fourth root of 16 times 3. Now I will use my properties of radicals to rewrite this as the fourth root of 16 times the fourth root of 3. And this is now 2 times the fourth root of 3. Okay, because 2 to the fourth power is 16. All right, so this guy became 2. Okay, that became 2.
Do we always have to go through like these steps, or can we go like through the first step and like
Oh,
back
yeah.
and step like 16, like, you know what I mean?
Yeah, no, you definitely don't have to be this explicit with your steps.
Oh, okay, okay.
Yeah, I'm just trying to be like, just go like a little slower than usual because this is new. But yeah.
Okay, I just didn't know for the homework.
No, you don't need to show all of these steps. That would be
Oh, okay.
as long as I see that you understand the rule. Yeah, it'd be good. Okay, so those are nth roots. Very good. And the final topic of the night. Fractional exponents. Okay, fractional exponents. Fractional, also called rational exponents. Okay. Okay, here we go. So let's just do some motivation. Let n be a positive number. How should we define this guy? How should we define a to the 1 over nth power? It's not immediately clear. What should we do with this? Okay, how are we going to give a definition to this guy? Okay, well, so let's just play around with this for a second. A to the 1 over nth power, if I raise that to the nth power, I can use the power rule. I can multiply the powers together. This is a to the n over n. And that's the same as a to the first, which is just a. So I hope you guys, so thus a to the 1 over n is an nth root of a, okay? Thus, a to the 1 over n is an nth root of a, by definition, because I raised it to the nth power and I got back a. So by definition, a to the 1 over n is an nth root of a. All right, so that's pretty cool. And that leads to the following definition. Thus, this is how we define it. Here's a definition for you. A to the 1 over n is the nth root of a. Okay? So I think that's pretty cool. So that's that. And now we just want to do a little more. How about this guy? How about a to the m over n? How do we do that? But that's going to be our last step in this direction. Okay, we can look at this two ways. We can look at this two ways. Okay, first way. A to the m over n. This is the same as a to the 1 over n to the mth power. Okay, and that's true by our power rule. If I multiply the two powers together, I would get back a to the m over n. But we actually have a definition for that inside of the parentheses. We rewrite that as the nth root of a, because that's what we defined a to the 1 over n as. Okay, so that's one way to look at it. And the second way, a to the m over n. How about this is the same as a to the m to the 1 over n. Okay, so I'm changing what I made the outside parenthesis, or the outside exponent and the inside exponent. Okay, but this is literally by definition the nth root of a to the m. The nth root of a to the m. Okay, because this 1 over n power tells us to take the nth root. All right, so those are our two definitions. So there we go. So thus, definition, here we go. So a to the m over n, this is going to equal two things, two equivalent things. It's going to be the nth root of a to the mth power, and it will also equal the nth root of a to the m. All right, we have two things for this guy, and they're both the same. So we have this one, and we have that one. All right, good. So let's just use this definition to simplify some stuff, and then we will call it a night. All right, so just before we finish, let me just remind you guys, the homework will be viewable after tonight's class. I will upload tonight's video lecture sometime tomorrow, and we're gonna have class on Thursday again. All right, and I hope most of you guys come again. All right, so that's just that, and now let's just do some examples. All right, so these are some kinds of questions you'll see on the homework. So write 343 to the 2/3 as a radical and simplify. Okay, so that's some kind of question you would see. Okay, so by definition, this is equal to the third root of 343, that whole thing squared. Okay, so I'm using definition 1. Okay, I'm using this guy. All right. But this is not bad because the parentheses is just 7. Okay, so that's just going to be 7 squared. Because if you do 7 to the 3rd power, you will get 343, and this is just 49. Okay. So that's that. So let me just write what I said. In practice, definition 1, so that first guy we listed, definition 1 will often be easier to work with, okay? Will often be easier to work with. All right, so that was just this. It was this guy right here. You take the nth root of a, and then you raise that whole thing to the mth power. So that's the easier definition to work with. Okay, good. So we'll do 2 more examples. So, sorry, I know that we're running over time slightly. I apologize. I think it was because of the welcome slideshow added some time. Okay, so here we go. Write 9 to the 5 over 2 as a radical and simplify. Okay, so I'm going to use definition 1 again. So 9 to the 5 over 2. This is the same thing as the square root of 9 to the 5th power. Okay, and this is simple because the parentheses is just 3, because that's what the square root of 9 is. That's just 3 to the 5th. Okay, and then if you want, you can write this out. 3 to the 5th is 243. Okay, but I'm certainly okay with you stopping right there. Okay. Good, good. And our final example for the night, this will be write 4 over the 7th root of a squared, so that crazy looking expression, as a fractional exponent. Okay, so we're going to go in reverse now. So we're going to rewrite something into a fractional exponent. All right, so let's just hone in on this expression here in the bottom. So just first, let's just look at that guy. See that the 7th root of a squared, this is equal to, in fractional exponent form, a to the 2 over 7. Okay, So I'm using the definition in reverse. I hope that's okay. Thus, our original guy, 4 over the 7th root of a squared, that's 4 over a to the 2 over 7. Okay, so I just replaced this with its fractional exponent form. Good, and you can stop here if you want. This is cool. Finish, but alternatively, you can bring that into the numerator and write it as 4 times a to the negative 2 over 7. Okay, because remember, anytime you move something from the top to the bottom or from the bottom to the top, the exponent will negate. Okay, it will turn from positive to negative or from negative to positive, depending on what its sign was.